Hey, it's Mr. K doing a video for AP Physics C Mechanics, and we're looking at some calculus and how to find the volume of a sphere. Looking at some different ways to do it, some ways to look at it, and so let's go ahead and start this problem off. We got a sphere of radius r, and in calculus, the way that we do things with integration is we add a bunch of small things together. And so what it is up for us to do right now is to figure out how we're going to split this into small pieces in order to add them together so that the sum of those small pieces would be the volume of the sphere. And so one way to do it would be to take individual small surface areas of spheres and keep on stacking them and stacking them and stacking them and stacking them and stacking them like a Russian doll. And if you added all those stacks together, then you should get the jawbreaker of a sphere, or gobstopper of a sphere volume. I'm not going to do that because we didn't go through and actually derive for the surface area of a sphere. But what we do know is we know the area of a circle. So the area of a circle is going to be pi r squared. And so we're going to try to work from that. And so starting with that, if we know the area of a circle, we can find the volume of a cylinder by taking the area of the cylinder or the circle, and we multiply by the height of your cylinder, which would give us the volume of the cylinder that we want. So I'm gonna work with little cylinders here, and I'm gonna split this sphere up into pieces that look a lot like this. And so each of these pieces is gonna have the same thickness, but of course as we start to get closer to the edge, our area is gonna go down, 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 because if you notice, it's like taking some floss and some cheese wire and cutting a slice out of a cheese ball, that these would be circular, but they would be smaller and smaller and smaller concentric circles. So, is concentric the right word there? Anyway, I don't need to do all these. So you get the point. So we're going to take one of these and we're going to model it here and try to work with that. So we have here is the area of that circle, which would be pi r squared times the height of that circle, which actually is this thickness here. And so let's define that thickness to be some kind of d something. I'm going to call it dr for right now. We might have to change it later on depending upon how this problem goes. So we're going to say the height is actually going to be a dr, and that should give us some volume, which is actually going to be a small piece of the volume, some dv. So if we did this, hopefully it works out. I'm just going to do a quick setup up here. And I'm going to say that we've got pi r squared dr, and we're going to add all those pieces together to get the full volume, because this is equal to dv. We're going to add all those together from 0 to all the volume. So let's go from halfway. So we might have to double this later on. So from 0 to the full radius, and let's just see what we get, if we get anything. So we get pi r squared. If you integrate, we get pi r cubed divided by 3. And we are going from 0 to r. So all this means is that we're going to plug in the top one. We're going to subtract it from plugging in the bottom one, and we get something. And that something would be pi, top one plugged in, cubed, divided by 3 minus 0. Because 0 plugged in, that would be 0. Now that is not the volume of a sphere at all. But what that is the volume of a cone. And so, yeah, we did this wrong. But I wanted to show you that you're going through these steps and you're thinking, oh yeah, we have these circles and I'm going to multiply by this thing. But you got to understand that what we're doing here is we're actually starting, let's say, in the middle, or even out here. But what we're doing is we're actually building up like a small slice and a bigger slice and a bigger slice and a bigger slice, and it's starting here, and we're doing that, which means we're actually going or, and that would be a cone, and that's not going to be a sphere at all. So that's wrong. All right. So let's go ahead and go back, figure out how we can do this again. Same idea. We're applying this to a bunch of small slices of things, but hopefully we can get it right this time. So we got to change some things. dr, we're not going to call it dr anymore. We're going to call this dx. Okay? And there's a reason why I want to do it this way. We could do it in spherical coordinates, polar coordinates, but let's just keep it with the x and y's. So if we do it dx, that means that this would be the radius of each individual circle that's going to be there, which is going to be the height, which is actually going to be not r because it's changing, it's going to be y. So what we have is this. We have the circle, which is pi y squared. That's the area of the circle. We need the height of these circles, which is now going to be dx. Okay. This is the same setup that we had up here, essentially, except now we're going to be using our usual Cartesian coordinates that we know. We're going to add all these together, and as before, this should be a small piece of the volume, and we're just going to go from 0 to all the volume, hopefully. Which means I want to go from, let's just do it this way. Let's go from 0 to r, here to there, and what we're going to do is, if you just saw what it did, that's only going to be half the volume of the sphere. Later on we're going to double it. Alright, so with this calculus, we can't integrate when we have these two things being different. This is y and this is x, and so I need to try to make them the same. So the way that we do that is to go back over here, and we need to figure out the relationship between x and y. And the relationship is the triangle, right? So this is x, and this is y, and the relationship again is Pythagorean theorem, x squared plus y squared equals r squared. Okay? And I want to replace this y, so I'm going to move this x squared to the other side. So y squared is equal to r squared minus x squared. So that's going to be right here. So I've got a 2 out here. I'm actually going to move that pi out there too. Constants we can move out of the equation there. We are integrating from 0 to r. We've got a y squared, which is now r squared minus x squared. And we're going to have this dx thing here, and it's going to be applying itself to both of those. Okay? So we have now the ability to integrate this. And we're going to integrate one term at a time. Okay, if you really wanted to see it, we can say 2 pi, the integration of 0 to r squared dx minus, I guess this is going to be a big parentheses out there, minus x squared dx, and the integration of that from 0 to r. And that 2 pi is on the outside of everything. So, first thing, r squared. What was r? R was not a variable. R is a constant. It is the radius of our circle, or our sphere. So this is going to go from r squared to r squared x, and it goes from 0 to r, minus x squared. X is actually the variable here. It does change. So x squared becomes x cubed over 3. And we're going to go from 0 to r. And let's not forget about our 2 pi that's on the outside. Okay? So what happens whenever you plug in r here, and what happens when you plug in 0? When you plug in 0, you get nothing. So I'm not even going to worry about plugging in 0. But I'm going to worry about plugging in r. So r plugged in here, I get r squared times r, which is going to give me r cubed, minus, I'm going to plug in the r there, r cubed, but we have a 3 on the bottom. And again, don't forget about the 2 pi on the outside. What is r cubed minus a third r cubed? And that's going to give us what, 2/3 r cubed? So this is going to give us 2/3, because we have 3 over 3 minus 1 over 3, 2 over 3, r cubed. And then we have this 2 pi on the outside, right? This guy. Well, 2 times, these are on top. 2 times 2, it's going to give us 4. Pi's there. We got the r, we got it cubed, and we're going to go ahead and divide that by 3. Solid line that, there you go. So this, hopefully, is the volume of a sphere. Up here, that was the volume of a cone. And it really, really does matter how you set these boundaries up and how you actually define the problem. Because when we set it up originally, we thought, oh, that's really fast. And some of you that had that little worksheet thing probably did that. And we're like, well, crap. Now what? Oh, we got to multiply by 4. Oh, we got to figure it. Yeah, okay, well, great. You can multiply by 4. You have a cone, 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 cone. Yeah, that could work. But really, when you do it right, you should get the actual answer without having to finagle it anyway. So there you go, 4 pi r cubed over 3, volume of a sphere. There you go. All right, we're done.